Hi, I wasn't going to record this today, but it was so quick and easy to get models working, I figured, just chuck it on, just do it. So how can we load model data? Well, if we search for Tiny Obj Loader, there's this cool project here, which it's a header-only C++ library, and it loads object models. So that's cool. So the way I would use this is go up here, download the zip, but the file we're really after is this one here, tinyobjloader.h. Okay, so we can build it from scratch if we want. We'll just grab this, does the same thing. Okay, so I grab that file and I chuck it in here. I should do that. Okay, so what was I saying? I chuck it in there. And now we can get to the job of actually loading things. So just pop up the top, and there's a few things I want to do. I kind of talked about this before, but I never really got around to it. We don't need this file, stbimage.cpp. All we need to do is paste that line there, and that's it. We don't need that file there, so we can go stbimage. Delete that, that's fine. Okay, so what do we need? Okay, cool. So we've got that one as well. And then we need to include that header file. Okay, awesome. So let's go down, and basically what we have, I also grabbed just a general object model to load in. So I've got this folder models, and in there I've got this statue.obj, and I picked a marble texture to put on the statue. So that's what we're going to load in and get it working. But if I load this in, it's not going to look very good without lighting. So I'm going to try to make some really basic lighting. For that, we'll need a normal as well. And we'll just update that. Okay, cool. Cool, so let's go to the shaders and update the shaders. Firstly, the vertex. This is vertex. Okay, so by default, the model matrix is a four-dimensional matrix. Four-dimensional matrix includes translations. We don't want translations, we just want to basically rotate things. So we're going to have this model, and as the model spins around, we want to spin the normals around as well. So we do have to transform them by the, you can see what I'm doing here. This is just taking the rotation part of the transformation. Okay, so then we go to the fragment shader. And why not? I'll do the full thing here. Okay, that looks good. So, what are we doing here? Well, sun direction is really kind of a direction to the sun, if that makes sense. And this dot product is determining the normal vector of a fragment. How parallel is it with the sun direction? If it's completely parallel, then the fragment is completely illuminated. If it is perpendicular or opposite to the sun, then that is 0. And this max is just capping it at a minimum of 0. Okay. Vec3.1 is just white light, so we take that amount times white light, multiply it. This is just coloring the fragment. Cool. Okay, so I just went ahead and did all the shaders, so we can probably compile them now. Okay, that's fine. Now let's get to getting the data into our program. Okay, so this is fine, but we don't need this data, right? Because we're going to load data, so we're going to set that to completely empty. Okay, so now we'll make a function to load the stuff. So basically we need to load that data in before we create the vertex buffer. Okay, so we've made this load model function. We'll just, it doesn't really matter where we put it, right? So let's put it here. Alright, so I'm just going to be a second. I'll type this up. Okay, so far so good. These variables up here are populated when the object is loaded, and then what we do is we start looping through the data and taking the data and chucking it into the vertex. Now, vertices is a completely flat array, meaning we have to kind of do some trickery to get at the individual components, but it's not too bad. This is just using offsets from a given index. Okay, so let's continue and get the normal and the texture coordinate. Okay, cool. Now the really useful thing about this tiny object loader, besides the fact that, hey, I don't have to write functions to do it by hand anymore, even though that is fun, the cool thing about this is it kind of parses the data and makes it like really straightforward. So if I want to, like, let's say for instance, well, first of all, I don't give myself a headache, but let's say for instance I want to create an object loader model, a model loader with a pre-transform If I know that I want to apply a type of transformation once, like flip an object upside down and then load it in, it really is no trouble just to pass this in and then transform things on the fly. Like, what I'm saying is it's very readable and it's written in English. The next thing we need to do is pass data in. Now, for the moment, we're going to use a very naive kind of strategy, and that is to assume that every vertex is unique. So we'll just load everything in no matter what. Okay, cool. So that's looking not too bad. We just need to go down to texture image and change that. Yeah, that's fine. Let's see if that works. So there it is. We have it. A little bit, I don't know, a little bit out of view though. So let's zoom the camera out a little bit. Go to update uniform buffer and we'll just set the camera's position a little further back. That's cool. So we've got lighting and everything, and we've got that white marble texture in there. That's looking nice. So just a few things I will add while I have the chance. I really should have done this earlier, but let's create a frame rate indicator. Yeah, why not? I'll just paste this in. This is a standard bit of code that I use in a lot of my programs. Okay, so what this does is it just measures the time right now, the time difference, and if we've gone above 1 second, then work out how many frames we've rendered in that time and reset everything. So we run this now. And that's pretty good, that's not bad. We're hitting about, above 6,500 frames per second. There are a few things we can do. So obviously we can just run the thing in release mode, which will apply more lightning to our silicon, and I mean that made a bit of a difference. We're now 8,000 frames per second. For a model of this many triangles, I mean that's good. I do have a beast of a graphics card running under the hood, but it's fine, it's good. Okay, so essentially this works, but the other thing I want to do is, remember, we were naively adding things in, naively incorporating every new vertex, but some of those vertices are not unique. So here's what we can do. This is a little bit ooey, but it works. By that I mean, I looked this up, I don't 100%. I understand the concept, I don't 100% understand the details. So let's say, and I am kind of just being humble, like I should stop talking. Okay, so we want to do is we want to track which sorts of vertices have been added already. Okay, so what this will do is it takes vertices as its key, and then its value is the index of the vertex, if that makes sense. So we've created this vertex here, and we've defined everything. The next thing we want to do is check if that vertex is already in our set. Okay, cool. So if we've got a completely unique vertex, then we set that as our key, and to the key we associate the current index. Then, of course, we add this to our set of vertices, only if it's unique. Then, no matter what, we do need to store that in our index buffer, because even if the point isn't unique, it's still being drawn. Okay, so this should cut down on our memory usage a bit. But there's a problem with this. We go to run this now, and it will complain. There's an error. And the error is we cannot count how many times a vertex occurs in this set if vertices are our key, because we do not have a way to check if arbitrary structures are equal to each other, and equality is also based on something called a hash function, which is pretty much associating a structure with a number, and then structures will be equal if their numbers are equal. Basically, we need a general equality test. So let's create that now. We'll go here, and we will override the operator, or define the operator actually, of equality. Okay, so that's all well and good. It's probably still not going to work. So run this again, and errors, because we need to define a hash function. Yeah, so hopefully this makes sense. We're really just checking if each of the component vectors are equal, and this fails because these are GLM vectors, and GLM vectors at the moment, well, in this implementation, they don't have an equality check, right? So let's go to the hash function. Yeah, let's do this first before we do the hash function. Okay, so of course, if we're going to be calling hashes on individual vectors, we'll need that, and we will also, apparently this is all experimental stuff, so we need to define what's cutting edge features. Cool, so we stick it into experimental mode, and then we go down and we bite the bullet and we write this damn hash function. Alright. Hey Andrew, I didn't realize we were writing Lisp. I didn't realize we were writing Perl. The horrible write once, edit never, bracket, 10th level of hell sort of stuff. Well, hey, I mean, there's an error. I'll fix that up in a second. But actually, let me just quickly check. There, you see what I mean? See what I mean about bracket hell? So that's fine. I mean, I just looked this up online. I just want the thing to work, right? We can learn about hashes later. Who cares? I just want to get my vertices. Okay, so you run this, and now instead of using like 70 megabytes, we're now on about 60 something megabytes, and our frame rate looks good. It's about the same, but I mean our memory usage is down, so that's good. Anyway, that'll be it for now. Hope you had fun, and yeah, all right, see you later. Bye.